All right, good morning, good afternoon. We're going to look at trigonometric identities today. So this is a new section for people. I don't suppose too many people have seen this. So by the end of today, I will be able to use the Pythagorean and quotient trigonometric identities to simplify algebraic expressions. Now that sounds really nasty and difficult, but what we're actually going to do is just solve some puzzles. And we're going to teach you a few of the rules of the puzzle. And that's what we're going to do. So if you view them as puzzles, they're kind of enjoyable. If you view them as problems, you might feel a little bit crummy. So before we start though, we're going to start with something called proving. So proving is a mathematical technique where you prove that one side is equal to the left side, or you prove that two things are not equal. And we do a little technique, and it's not that complicated, but LS stands for left side, and RS stands for right side. Okay, and so what we're going to do is we're going to cut our problem right on the equal sign. So our left side is 8 plus 2 all squared minus 4 times 5, and our right side is 4 squared times 5. So this is, let's make that a little bit better, 4. So all I'm going to do is I'm going to work with my basic algebra skills, my BEDMAS, those types of things, and try and make the left side and the right side eventually have the exact same number. So if I do my brackets here, I've got 8 plus 2 is 10 all squared. 4 times 5 is 20. And then 10 squared is 100, minus 20 is 80. Okay, so now if I can make the right-hand side equal to 80, then I've proven that this statement is true. It's equal and it's true. So that's the goal. So if we look here, this is 4 squared, so that's 16. 16 times 5 is 80, and we have the same value, so therefore left side equals right side, and we have done our first proof. Doesn't have to be overly complicated. It's just a nice little strategy. We tend to cut it at the equal sign so that we don't get terms jumping over the equal sign, which causes some other problems. So all of our proofs we're going to cut on the equal sign. That's going to be the way we're going to approach them. So we have something like this. Prove the following is true or false. So we have some quadratic information here. So I can write out x plus 2 all squared is my left side, and x plus 1 x plus 3 is my right side. I can FOIL out the left-hand side, so x squared plus 3x plus 1x plus 3, and end up with x squared plus 4x plus 3. Now, I don't have to get to this stage. I could have worked on the other stage and tried to turn it into these two factored binomials. It's kind of an open solution. All you have to do is make sure that your last lines are exactly the same, and you've proven that the identity or the proof is true. So if we look at this one here, this is 2 brackets of x plus 2. So I'll just write that out real quick because I know it's easy to make mistakes doing that. FOIL out the x plus 2's, x squared plus 2x plus 2x plus 4 minus 1. Collect like terms. So 4x plus 4 minus 1 is just 3, and it's late at night, but I'm pretty sure I did that one right. So if we see x squared plus 4x plus 3 on both sides, so we can say this is a true statement. The left side equals the right side. All right. So to prove trigonometric statement is true or false, we need a few more tools. So we have our primary trig ratios, we have our reciprocal trig ratios, but we're going to get a few more tools involved here. And some of our problems are going to be a little bit more complex, but that's what makes it fun. So we're going to prove our first thing called an identity. And it's called a quotient identity. Quotient means some sort of division. So I have a right triangle here. I'll just put my right in here. If I come over to sine theta, theta being this corner right here, then sine theta is y over h. Cos theta is x over h. And tan theta is y over x. And none of that should be surprising. We've been doing that for a few days, so that should be comfortable. What's new is we're going to isolate the x and the y. So over here, I'm going to actually multiply both sides by h. And then these h's will cancel, and I'll be left with y equals h sine theta. And I'll do the same thing down here. I'm going to multiply both sides by h, These will cancel, and I'll be left with x equals h cos theta. And now here's where it gets a little bit different. If you look down here at tan, tan is y divided by x. But if we look up here, we now have a different way of expressing y and x. So what I can do is I can take my tan theta, and instead of having a y on top, I can actually write h sine theta. And it looks something like that. On the bottom, instead of an x, I can write h cos theta. And now something should jump out really quickly at you. Do they both have an h on top and bottom? So these h's will cancel. And what we've just generated is a new relationship called an identity, called the quotient identity, and it is tan theta is equal to sine over cos theta. So this is a true statement, and you're welcome to test it. So anytime you see a tan theta, you can replace it with sine over cos. If you want to do a quick little test, take a theta value and substitute it in. So try theta equals 60 degrees. So tan 60 should be equal to sine 60 divided by cos 60. So take a second and punch it in your calculator and see what you get. Okay, so I punched in tan 60 into my calculator, I get 1.73. I punch in sine 60 over cos 60, and big surprise, I get 1.73. Okay, and you can do that with any angle because this is a true statement. Okay, this is almost like a law if you want to think of it that way. There are a few little things we have to worry about, but for the most part, this is rock solid. And this is called the quotient identity. Now, the quotient identity can be expressed in different ways. Tan theta doesn't have to be by itself. You could also express the quotient identity if you rearrange the terms to look something like that. So I've multiplied both sides by cos theta, but this one's a lot harder to remember. So we tend to focus just on this one. It's called the quotient because there's division, and most people are very comfortable just remembering that tan equals sine over cos, and if you have to, you can always do the algebra on the side of your paper later. So that's our first identity. This is our second identity, and we're only doing two. This one's called a Pythagorean identity. So I have my same triangle. My sine is y over h. My cosine is x over h. And my tan theta is y over x. I have Pythagorean theorem because this is a right triangle, so Pythagorean theorem holds. And now I'm going to do something a little bit radical. And this is where math proofs are kind of fun to watch because they're very creative. I'm going to divide everything by h squared. So if I write x squared over h squared plus y squared over h squared and h squared over h squared, so as long as I've done the same operation to both sides, I'm maintaining equality. And now something happens here. I'm just going to rearrange this using some of our exponent rules. So x over h all squared is the same as that line, plus y over h all squared is the same as that term, and h squared divided by h squared is just 1. And now I'm going to take my isolated trig ratios on the side here. So notice x over h, x over h. So I'm going to replace x over h with cosine. Okay, so I'm going to go back in here, grab a pen, not a crayon. And so this becomes cos theta in a bracket all squared. Y over h is the same as sine, and I've got them backwards in my formula, but that's okay. It's just additive. And there is our Pythagorean identity. So I have them a little bit backwards. I put sine first. That's okay, not a big deal. So sine squared theta plus cos squared theta equals 1. So please notice, both of these are correct the way they're written. Usually, though, the little squared term is written inside on the sine. That can be a little bit confusing for some people, so just make a little note of that. These two things are exactly the same. Okay, and now It doesn't always have to be written this way. We can use our algebra skills and we could say, well, sine squared theta is equal to 1 minus cos squared theta. That's still a true statement. It's just a rearranged form of the Pythagorean identity. And so the good news is we're only going to do the two, identity. In grade 12, they add a couple more. Okay, so this one has a couple variations. And I'm going to show you one more variation on it just so you can see how they're generated. Back here, I divided by h squared. So this one, I'm going to do everything exactly the same, except I'm not going to divide by h squared. I'm going to divide by x squared. So sine theta is still y over h, cos theta is still x over h, tan theta is still y over x. Now I'm going to divide everything by x squared. So I'm just going to cheat a little bit and write it up here for the interest of time. Okay, so now x squared divided by x squared is 1. Y squared divided by x squared is y over x all squared. And h squared over x squared is just h over x all squared. Now, the first term is easy. That's just a 1. The second term is not too bad because y over x, we can see that over here. So this becomes, sorry, not there, down here. This guy down here. Whoops, there we are. I need my eraser. So y over x can be written as tan. So this becomes tan theta all squared. And now the last one is a tricky one, and this is where we have to go back to our reciprocal, our reciprocal relationships. X over h, okay, it looks like cos, but the letters are backwards. Okay, they're upside down. So that actually becomes secant all squared. So this is another form of the Pythagorean identity, and it looks like this. 1 plus tan squared equals secant squared. And there are a couple of dead giveaways on how to spot a Pythagorean identity. One, quite literally, if there's a 1 involved, that usually is a bit of an indicator. And 2, if you see squared terms in there, you want to start thinking, well, a Pythagorean identity might be involved here. So let's put them into practice. And we'll do 4 examples here, and you'll see how they roll. So this is my tan theta times cos theta equals sine theta. I want to prove this to see if it's correct. So I write out my left side. There's tan theta times cos theta. And the right side is just sine theta. So now the right side's nice because it's all by itself. It's about as isolated as we can make it. So that actually makes our life a little bit easier. So I'm going to focus on the left side. And when I look at this tan theta, I'm going to think, you know what? I have an identity for tan theta. I have the quotient identity that I can replace tan theta with sine theta over cos theta. That's a completely legitimate move. Totally allowed. And now I have two things multiplied together. If we need to, we can put a placeholder in here just to keep track of things. So the cos theta is on the top. And what we see is, hey, there's a cos theta on the bottom and a cos theta on the top. Those two things cancel, and I am left with sine theta, which conveniently is exactly what I have on the right side. So this identity, or sorry, this proof is true. The left side equals the right side, so we are true. And that's all you have to do. Now, obviously, they get a little more complicated. We have a little bit of fun with it. You have a few more steps to do, but that's the basic principle. So let's have a look. You can pause it if you want to try it first. There's a couple things that are going to jump out, and I'll point those out as we go through. So there's a tan theta on top over a cos theta. Over here we have sine theta divided by 1 minus sine squared theta. So before you start, you want to do a little bit of thinking, because a little bit of thinking goes a long way with these. If I compare the left side and the right side, we can see very quickly that the left side has a tan in it. But the right side does not have a tan. So in the interest of trying to move this forward, I need to get rid of that tan. And then everything will be written in terms of sine and cos. Okay, so let's try that. So we're going to replace tan theta. Okay, and I'm just going to write it this way so you can see how the algebra works. Tan theta times 1 over cos theta. These two things are exactly the same. All I've done is I've pulled the denominator out. I'm just multiplying by 1 over cos theta. It's the same thing. And what it does is it allows me to look at tan theta and replace it with sine theta over cos theta. So keeping track of your fractions, keeping track of the numerators and denominators is really important. So now if I take these two terms, they're multiplied, which is awesome. If I multiply across the top, I get sine theta. If I multiply across the bottom, I get cos squared theta. So my tans are gone, which is awesome. So now let's go over and look at your right side. Well, the right side is written just in terms of sines. So this one on the left side has a cos in it. So we have to do some work here. And some things jump out at me because I've done a lot of these. Right away I see this dude. I see a squared term. And so what I start to think about, is there a Pythagorean relationship that could get rid of that sine squared? And more importantly, is there a Pythagorean relationship that might even get rid of 1 minus sine squared? So if we just jump back here for a minute, take a look. Sine squared theta equals 1 minus cos squared. So there is a way to rearrange these. So if I look at this one, the bottom, I'm going to leave the top alone. The bottom can be replaced with cos squared theta, which is a Pythagorean relationship. And now if we compare the two, are they the same? And the answer is yes. So therefore the left side equals the right side. It's a true statement. And there are a lot of different ways to solve them. You don't have to have the same line as your neighbor. All you need to end up with, though, is the left side and the right side have to be exactly the same. Okay, without breaking any of our algebra rules. Okay, let's try one more maybe. Woo, okay, so this one's got lots going on. So 1 minus cos squared theta, that's our left side. And the other side has got 3 terms multiplied together. And you might already have some ideas on what to do. So if I compare the two sides, immediately I see on the right hand side I have a tan theta. I don't have that tan theta on the left hand side. So that's the first piece I'm going to go after. I'm getting rid of tan theta. So I'm going to have sine theta times cosine theta, and then I'm going to replace tan theta with sine theta over cos theta. And then I'm going to take a line and just clean it up. Well, what do we notice? Well, there's a cosine theta on top and bottom, so those actually cancel. So I'm left with sine theta times sine theta. Well, that's sine squared theta. Okay, so I've got that one worked down pretty small. I am noticing that, hey, look, there's squared terms in both of these. So there's probably a Pythagorean theorem, a Pythagorean identity that's going to tie these together. So we might recall that 1 minus cosine squared is just sine squared theta. And lo and behold, we are done. Okay, so familiarity with spotting the relationships is really cool, really key. But that doesn't mean you can't have strategies. So my strategies when I solve these look like this. And you heard me and saw me do some of these, so I look for tans right away. So if I see tans, there's a good chance I'm going to go after getting rid of that first. So that's the first thing I always look for. It may not be the best move, sometimes it backfires, but I've found in my experience it works really well. I also look for squared terms, because squared terms are going to tell me that, hey, maybe Pythagorean's involved here. And this one's a little tricky. Compare the number of terms. So if I just jump back here for a second, you can see how this side here had 3 terms. So, and the left side only had 2 terms. So I'm looking for ways on how I can combine them. And then while I'm looking at how I combine them, I'm also looking at the operations. This guy is multiplied, this guy was subtracted. So I have to do something about that. I need them to all be multiplied, or I need to have subtraction show up on the right hand side. So all of the hints and the tips on what to do are actually buried in the question. And then we can compare the denominators. Okay, so you look at the bottom and you say, hey, what's the bottom on this left side? What's the bottom on the right side? There might be a hint on what you should do there. And that's using trig identities in proof. So let me backtrack. So there's a couple questions to try. Understand you will have problems. It won't work. You'll get frustrated. That's absolutely fine. That is expected. So try them. You might take 5-10 minutes on one question. Your neighbor might do it in 30 seconds. It doesn't mean they're smarter or better than you. It just means they saw the pathway a little bit quicker. Again, you just keep trying. The more you see, the easier they get. All right. Thank you.